So we have 2 weeks left, and the next Friday will be final exam. So with today, we have 5 lectures, right? Which means I'm going to finish chapter 18 and 19 in the next 5 lectures. I'm going to give you homework. It's going to be a little squeeze. That's how all summer courses are, because we're getting too close and the exam is technically in the same week that we do stuff. For this chapter, I posted the homework today because you had a quiz. But for the next chapters, I'm going to post it when we kind of progress. Like chapter 18, I probably post the homeworks by Wednesday, so you can start working on them at the same time. Okay. The other thing is we can have one more quiz next week, next Monday, covering chapter 17. Okay. It may look too much because on Monday you have a quiz, on Friday you have final exam, but I think you're going to have to study for final exam anyway. So reviewing chapter 17 for the quiz when you have done your homework could help you. Also, one more quiz could balance if you have like a bad day in one of those things. I'm not going to exclude any quiz. Some professors usually drop the lowest grade. I don't do that, but if you have more quizzes, if you have one bad, it's less, effective, your final grade. Is it a good plan? Okay. Now we're going to start chapter 18, which is about the work energy. Let me share the screen. I think I mentioned a few times, whatever we did for particles, we're going to do for rigid bodies. We start with kinematics, chapter 12, particles, chapter 16, rigid bodies. The difference was when you have rigid body and the size of the object matters, then moment of inertia comes to play and rotation comes to play, right? For particles, we didn't talk about rotation. When it was a car was like a point on your GPS moving around. But now when we have objects that their dimension matters, you're going to have moment of inertia, you're going to have torque or moment, like in equivalent of actual force for the particles. And you had rotational motion, angular displacement, angular velocity, angular acceleration. In chapter 13 and 17, it was Newton's second law. The whole concept was identical, except when you have rotation, the torques and moments create angular acceleration, right? M about G equals IG alpha. We did some examples of that, and you're going to do more with the homework. Now we're going to talk about work energy. The question is, does the size of object, the rigid body, affects work energy or no? You may have seen in the past 2 chapters, the overall principle of motion applies to the particle and rigid body same way. But the difference is when you have rotation, another term, another equation is created. We're going to see how that affects the work energy in this chapter. Does that make sense? So be ready to see a new term in energy equations, right? So what we're going to learn here is how to find the kinetic energy of a rigid body. Because rigid body could have a combination of rotation and translation. Then we're going to determine how we can find the work of a couple, and couple, you guys remember from statics, 2 equal opposite forces, right? That's a couple, not like a family couple. Then we're going to get the work energy relation based on those things and conservation of energy. So you're going to see these 2 parts fundamentally is identical to chapter 14. Nothing is new. The conservation of energy is the same. The work energy relation is the same. The only change is if you have angular motion, how you can calculate the work of, again, I'm going to use the phrase which is wrong, but kind of for analogy, angular force, right? Linear force times displacement is work. We want to see if you have angular force, which is technically torque, moment couple, how you can use that and calculate the force. The rest is going to be the same. Calculate the work, sorry. Now, to get the kinetic energy of a rigid body, assume that you have a rigid body that has a combination of translation and rotation. So this kind of potato-shaped rigid body has general motion. The entire rigid body has one omega, but each point could have its own velocity, right? To analyze this, like chapter 17, we're going to have to put our reference somewhere. So we choose point P with velocity of Vp, and we get our x and y here. So for any particle like I, its position is x and y from this, or the position vectors, or this is all like relative motion stuff. So if you want to find the kinetic energy of the system, you can assume that this is a system of particles, right? Each, of course, what you see here is a continuum system, but each part is a tiny particle with its own velocity, right? So if you find kinetic energy, half mv squared for all those particles, and you add them together, and this is going to be your kinetic energy. Can you guess where we go from here? If we use relative motion analysis, we're going to get each velocity in terms of Vp, relative position, and omega. You expand that, and I'm not going to go through derivation. It is in the textbook. If you're interested, you can have a look at it. You need help, let me know. But usually, students are not interested in derivations. I just stick with the, you know, the basic concepts and the final results. So if you get V in terms of Vp and omega and relative R, which is this R, and expand it, you're going to get your overall kinetic energy like this. This is kind of similar to the expression we had for torque and alpha, remember in chapter 17? So the kinetic energy of the system, half mv of p, because p is the point we know its velocity. This y bar and x bar are not for I, are the position of center of gravity, similar to what we have before. And I about p is the moment of inertia about the omega squared. So you're going to see that in addition to linear velocity causing or creating kinetic energy, the angular motion omega and angular inertia, again, that's not the proper expression, but let's call moment of inertia like angular inertia, IP, contributes to the overall kinetic energy of the system. Looks complicated. Specifically, you see this is VPX times Y bar, VPY times X bar, and one of them is negative, one of them is positive. I can never memorize something like this. I can memorize something complicated, but it's like two of them, and one of them is negative, positive. There's no way to remember which one is which one. Of course, you can have your formula sheet. If you're at work and get to this point, you can Google it and find everything. But remember, we had something similar for force and moment and acceleration, and we simplified that. Is it possible to simplify this? Hopefully we can simplify that, right? Now, any question about this expression? That each term means what? VP is the velocity of point P. Omega is the omega of the whole rigid body. M is the mass, obviously. As I said, this is VPX, X component of velocity, Y component of velocity. That's easy to understand. Y bar and X bar are the position of center of mass. Remember, in the picture here, X and Y are for an arbitrary particle I, but if center of mass is here, this is going to be X bar, it's going to be Y bar. We had this in the previous chapter, right? And I omega, this I is about P. You remember, I should be about a point. Unless mass, which is a single number, moment of inertia depends on the axis of rotation. So that is what we get here, right? Now, this is the equation we have. If you have translation only, see what happens. For translation only, there's no omega. So this term, and this term will vanish, right? So your kinetic energy is technically like half mv squared, which is something like a particle. You see, when you eliminate rotation, the rigid body turns to a particle. We saw that in chapter 16, we saw that in chapter 17, and now here, the kinetic energy is just half mvg squared. Any question? Now, this is one case that you have only translation. Now, if you have only rotation, what is only rotation? Means like the object rotates about a fixed point. If I put my point P on that fixed point, O, then velocity of P will be 0. This term, and this term vanish. Your T is going to be half I-O omega. O is the fixed point around which the rigid body rotates. Make sense? Colin, looks good? Now, if there is general motion, no translation or no rotation, then I can simplify this. How? Similar to chapter 17, one special case could be if I choose my point P on the center of mass. I want you guys to look at this and tell me which term will vanish. If P is center of mass, which term will vanish? I'm going to ask Heizi. Which term or terms would vanish?
I think VPX and VPY, both of them will vanish.
These two terms?
Yes.
Why?
Because P is the center of the mass, and I think it won't move, and so it doesn't have the velocity.
Hold on. In general motion, center of mass doesn't move. The whole thing moves. Let me ask Yoon. Yoon, which term could vanish? Actually, Heizi's answer was correct. The reasoning wasn't correct. I want to see if you can spot why these two terms will go 0, but why? And if Yoon doesn't know, I'm going to have to go to the majority.
I don't know.
Callie.
If P is the same as the center of mass, X bar and Y bar would be 0.
Exactly. We did the exact same thing in the previous chapter, right? When P is on G, Y bar and X bar are 0. So these two terms will vanish. And if these two terms vanish, P is G, this term becomes half mvg square, and this becomes half ig omega square. So technically, this is a long expression, but for translation only, you can use this. For rotation only, you can use this. And for general motion, you can use that, right? And let me remove the word pure here, because I think we should put translation only. Okay. So this is how you get the kinetic energy. Before we move forward, let me ask you this. In chapter 14, we talked about the work of some famous forces like gravity, spring, friction. When you have rigid body, does it affect, for example, the work of friction? Or the work of a spring? Yang, when we have rigid body attached to a spring, how we can calculate the work of a spring? Is it any difference between particle and rigid body? Anyone? Remember, when you have a rigid body attached to a spring or anything attached to a spring, the energy is stored in a spring, or the work done by a spring only depends on its elongation and compression, right? It doesn't matter what is the other side. The friction force, friction times displacement is the work. For the gravity, each particle is different place, but that is how we use G. So mgh or delta y is measured from center of mass. All of those terms are the same as the way it was for particles, right? The only change was this kinetic energy, because angular motion creates extra kinetic energy, as you can see. And in terms of work, there's one more addition to this, and that is the work of a couple. So you know that a couple is a pair of forces that apply in opposite direction and equal force. The question is, if this rigid body has some translation, how much work this does? Look at here. If I move this, for example, to this side by a small ds, and please look at here for a second. This force and this displacement are in the same direction, create a positive work. This force and displacement are in opposite direction and create negative work. Because the two forces are the same, F times ds and this F times ds are the same opposite direction. So technically, either you get F minus F times ds, or FDS minus FDS equals 0. So when you have a couple, which means two equal and opposite force, if the rigid body only translates, the work of the couple due to translation is 0. Does that make sense? Based on this derivation? Chris, does it look good? Okay. Now, let's see what happens if we have rotation. For rotation, look at here. If this rotates by d theta, let's say this is the center of rotation between the two forces. This is d theta. This is same d theta. This is half a distance. This is half a distance. So for small d theta, ds is going to be d theta by r2. Let me do this in tablet so I can write it step by step and you can follow better. And then we're going to come back here. I think I need to make some changes apparently. Hold on. Okay. So suppose this is your rigid body and this is your couple force. Equal and opposite direction, right? If this rotates a little bit, this is going to be d by 2. This is going to be d by 2. If the whole distance is d, this angle is d theta, and this angle is also d theta, right? Now, if I calculate this distance, which is how much this force is displaced, ds is going to be d by 2 d theta, okay? If I calculate this distance, which is how much the other force displaced, it's going to be d by 2 d theta. So the two ds's are the same, right? Let's just call it 1 and 2. I think it's the way that book calls it. However, look at here. This displacement, if this force is this way, oops. If this force is this way, this displacement is the same way. For the other force, this is this way, your displacement is same way. So technically, the two forces and displacement are in the same direction, unlike the translation. If that's the case, if I want to find U12, I'm going to have to get integrate of f ds, right? This is going to be d by 2 d theta, right, times f plus d by 2 d theta by f, right? Why? Because this is a positive work, both of them same direction. This is also positive work, both of them are same direction. So if you simplify this, you're going to get d by 2 and d by 2. If you factor everything, right, you're going to get is equal to d f. Let's just put it f so you don't feel d is like differential. F times d theta. This d, the distance between the two objects, is fixed. If the forces are fixed, constant forces, they don't have to, but if they are, then you're going to get fd times integration of d theta. So we're going to get fd delta theta, right? And fd, if you go back to the definition of couple, fd is technically your couple m, which means U12 is going to be m delta theta. Now, if m is variable, U12, you can write it integration of m d theta. Now, let me ask you this. we have vector sign here, right? Why we don't have vector sign here? Because technically this should have been a dot product, right? Why I don't use vector sign? Anyone knows? Haojin, why we don't use vector sign here?
I don't know.
Well, you can. Actually, I did here, right? But remember, when we talk about 2D motions, all couples are in Z direction, all thetas are Z direction, right? So Z dot Z, because the angle is 0, cosine 0 is 1, technically turns to regular product. So you don't have to use dot for Z. If you do 3D, if you have a robotic arm that moves in a space, M and theta may not be in the same direction, then you have to use the dot. But with all applications we have had so far, chapter 16, 17, and now, the motion is in a one plane. Every moment and theta, d theta are perpendicular to the plane Z direction, so you don't have to do it that way. If you put it, it's okay, but technically, you see this is what happened. Your M is M times K dot d theta times K. So technically you get M d theta K dot K, and K dot K is 1, right? That's how it goes. Any question? So for the translation, the couple did not create any work, but for rotation, they create a work that comes from angular displacement times couple. That is why sometimes I like to use the word angular force, because there's a still analogy here. You remember we had everything from the beginning, S theta, V omega, A alpha. Now you have F, you have moment or torque, same, right? Your work is F ds, here is M d theta, right? Your kinetic energy was half mv square. Here you have half mv square plus half I omega square is kind of added. But up to here, for everything you have linear, you have an equivalent of rotational version, right? So for force, we don't call it rotational force, we call it torque, moment, or couple, but it's technically, and also for inertia, you have mass here, and you have I here, like IZZ or whatever. Does that make sense? So with this analogy, when you have work, you can find the work of due to rotational motion and torque, couple, everything. So if this is what we did. This is just the same thing. F, I said R d by 2 here, it says R by 2, doesn't matter. R by 2 d theta, because both of them are in the same direction, are positive, you write it this way. FR is M, d theta stays. So you get the integral. For 3D motion, you can use the vector. For 2D, you can use vector, but it's just already ZZ for both axes, so no big deal. Any question about this? So these were the main differences between particle and rigid body. Your kinetic energy has an extra term due to rotation, and the work you calculate brings the component from moment and rotation. Any question? Looks simple. Kelly, is it easy? Or you guys are too tired? It's like Monday morning. You're not supposed to be tired, right? Okay. Now, let's go to the next part. We're going to do the work energy relation. As I said, the work energy relation, the overall concept doesn't change based on particle or rigid body. So technically, the initial kinetic energy, all the external forces, now we say and moments and couples, the work of forces and couples gives you the final kinetic energy, right? This is exact same. You just, when you calculate your kinetic energy, you have mv squares, you have I omega squares. When you calculate your work, you have F times displacement, you have torque or moment times angular displacement, and you add them together. Remember, this is a scalar equation, so everything is a scale, just a number. Right? So your kinetic energy has two terms, your work has two categories of terms, force displacement, moment angular displacement. Any question about this? Now, if there is no non-conservative force, remember, you can still separate this with conservative and non-conservative, right? Let me write this down in the tablet so we can kind of easier, follow that. So when we write the expression summation of initial kinetic energies plus all work done from 1 to 2 is the summation of final kinetic energy, this work still can be divided into work of conservative forces and work of non-conservative forces. And when I say forces, of course, forces and couples, moments. Right? The conservative forces, what were the conservative forces? Gravity plus spring. Right? So if I separate that, I can take this to potential energy and turn it to V1 going to V2. Initial potential energy turning to final potential energy. Remember, when we defined conservative force, it was a force that it works doesn't depend on the path of motion. It was gravity and a spring. It still applies. Doesn't matter if that spring is attached to a tiny particle or a large rigid body. It's the formation, its force, everything is going to be the same. Same with gravity. The only thing is for a particle, you had this particle going like position 1, going to position 2. For a rigid body, it's like this. This is G. This is position 1. Goes here. This is 2. So we measure Y1 and Y2 from center of mass. Okay? That's the only difference. Now, non-conservative forces give you summation of work of non-conservative. Right? So if I substitute these two, look at here, this term and this term, if I replace it by that guy, then you're going to get summation of T1 plus U, sorry, plus V1 plus summation of U1 to non-conservative is equal to T2 plus, let me make it a little smaller. Okay. And this will be the principle of work and energy. It's exactly same as before. The only difference here, you have md theta, and here you have half mv squared plus half ig omega squared. Okay, the rest is the same. This wouldn't change for particular rigid body. Does that make sense? Do you guys remember this stuff from like 2 weeks ago? Yes? No? Your faces is not convincing. Yes. Okay. Now, what happens if there is no non-conservative force? And remember, when I say force, is a general force, force, moment, torque, everything. Right? If there's no non-conservative force, this term will vanish. And if that vanishes, what you get, summation of T1 plus V1 equals summation of T2 plus V2, which is conservation of energy. Right? So you can use it if there's no friction, no pulling, no pushing, no torque from an electromotor or things like that, then this guy will go away and you can write it like that. Looks good? Any question? Colin, does it look good? Everybody? I have a good news for you guys. Chapter 17 finished. That was it. Kelly looks confused. Let's go to the slides, see what happens. So this was the principle of work and energy. If there's no non-conservative force, you separate the conservative, non-conservative, you get a V1 and V2, and that's it. Just one stuff that you remember, when we have rolling objects, things move, your static is not kinetic, right? When things roll, your static is still friction, right? Your friction is friction, but it's static, and the static friction does not move, so that does not create any work. So if you have a tire drifting, that is kinetic friction times displacement gives the work. But if your tire is rolling, because that's a static friction, no work. That's another things to remember, right? So when things go like that, and this is the rolling point, it says IC, which reminds you IC stands for, you know, no sliding here. Then this doesn't create any work. Make sense? We are done with chapter 12. You can go home now. Right? Not really. Let's do some examples. Okay. Any question about the whole concept? I'm going to review quickly. We defined kinetic energy for a rigid body, right? If it translates only, if it rotates only, or if it's general motion. We have those three cases for the kinetic energy. And we define the work of a couple or torque or moment, whatever you name it, m theta. Everything else is identical to chapter 14. Conservation of energy, the principle of work and energy, conservative and non-conservative forces, they're all general concepts. It's just when you use it for rigid body, you have this couple of more terms to consider. Looks good? Okay, now let's do some examples. You see 1, 2, 3, and we're done. So before these things, and I didn't do that example because I thought the course content is so short, we can continuously moving. Let's see, you have a mechanism like this, and you want to find its kinetic energy. Okay? So you have three links. Link AB rotates about fixed point. Link CD rotates about fixed point. Link BC has general motion. The mass is not given, but the weight per unit length, it's like these are same profile. The weight per unit length is given. So you can calculate the mass of each. Omega of AB is given. So based on omega of AB, you have to find all the velocity components. And from there, you can get your kinetic energy. See how this works. Let me draw this in the tablet and you guys do the same. So one of them is 3 inches, the other one is 4, and the other one is 5. AB is vertical, BC is horizontal, and CD has 45-degree angle. So the weight per unit length is 0.5 pound per inch. Omega AB is given as 2 radian per second. And you want to find the kinetic energy of the system. Yeah, I don't think we need any other. Okay, 3, 4, 5, 3, 4, and 5 inches are the length. Let's go to the tablet. So this is technically how the problem looks like, right? 3 inch, 4 inch, 5 inch, right? Weight per unit length is given. Omega AB is given. First of all, let's find the mass of each of them, right? So M, you know what, let's just go, doesn't matter. We know that we need masses. So MAB is going to be 0.5 times 3, which is its weight, divided by 32.2. MBC is 0.5 times 4 divided by 32.2, and MCD 0.5 times 5 divided by 32.2. Do you guys have the numbers for these three? Zero point 0.0467 slug. Zero point 0.0621 slug. Zero point 0.0776 slug. Do you guys get the same number? We didn't
I
check.
got
You got the same number? Okay. So these are the masses that I need. Now let's see how much is the kinetic energy of the system. T of the whole system obviously is going to be T of AB plus T of BC plus T of CD. You add the kinetic energies of every single term to get the final number. Now, what kind of motion AB has? I said it before, but what kind of motion AB has? Come on, guys.
Rotation.
Rotation. So for AB, if it's rotation, TAB is going to be half I about center of rotation omega square. Okay. I'm going to get each of them one by one and then calculate the values and go forward. Okay. For BC has general motion. So we're going to get half MBC VG square plus half IG omega BC square, and this should be omega AB, obviously, right? For CD, again, rotation about fixed point TCD is half IC omega CD square. Any question about this part? This is just what I took from the equations, the formula I gave you. Okay, now, what is I about A? Let's call it 1, 2, and 3, right? For 1, omega AB is given. All I need is IA. So IA, the moment of inertia of a slender rod about is H or is N. Do you know how much is it? Some of this you may need to kind of memorize it so it saves your time. I see Callie is trying to find it in the textbook. So Callie, you tell me. What did you get?
I'm kind of confused because it doesn't list like an IZZ, but it has like an IZ prime Z prime, but it says 0.
Okay. I don't have the textbook with me, but if Z is the axis of along the length of this, how much is the distance of mass from the center if the dimension is negligible? Is 0, right? Remember, moment of inertia is md square or mr square. R is 0. So if you have a slender rod, moment of inertia about the axis is 0. But when you rotate like this, I don't know if you can see my hand, right? This is the axis of rotation. It could be X, X, Y, Y in the textbook. If you look at that, it's going to give you ML squared by 3. And if you substitute this, we're going to get 0.0467 times, remember, the dimensions are in inches, you have to make it feet. So times 3 divided by 12 by 3. Let's see. You should get something like 0.00389. Is this correct? And the unit is log foot cube, foot square. For term B, let's just use another color. Let me, you know what? Let me just pick this and change the color code. So we're gonna go with red now. Okay. MBC is simply, maybe have it, right? VG, we need, IG, we need, omega BC, we need. Now, IG, look at here for a second, please. G, center of mass, is in the middle, right? If you go to the same textbook stuff to find I of this slender rod about G, this is what you're going to get. IG is M L squared divided by 12. Okay. And if you substitute the numbers, you have 6 to 1, 0.0621. Oh, hold on. I made a mistake here in the previous one. We missed the square here. So this is not correct. You have to multiply this by 3 and divide it by another 12. Sorry, my bad. So we're going to get 0.000973. And here, the length is 4, so you're going to get 4 by 12 square divided by 12. So 4 divided by 12 square divided by 12 times 0.0621. And you're going to get 0.003 zeros 575 slug with square. Now the question is how I'm going to find VG and omega BC. How I'm going to find this guy. Look at the mechanism. We have a moving mechanism. I want to find this omega BC and velocity of G. How do I do it? You can use the vector analysis from kinematics, okay? Or you can use IC, the way we use in the quiz, right? Which one you prefer? I think IC is easier. Otherwise, you have to write the equation once for C, once for G. You have to do all the vector analysis twice. So if that's the case, let's go to IC. I hope this is fresh in your mind because we just did it like an hour ago. Velocity of B is going to be in this direction. So perpendicular to velocity is going to be this line, right? Let me put this B here. Then velocity of C is going to be in this direction. Perpendicular to that, it's going to be this line. And when you draw the line, this is going to be your IC. Okay? And this angle is 45, which means this is also 45. Right? You guys follow? I'm going to have to move this down to write everything based on that. Otherwise, it's hard to follow. Going up and down. Okay. Now, if I use IC, look at here for a second, please. I mean, you had this quiz just a few minutes back, but I'm going to repeat it, the procedure, how you solve it. You need to have the velocity of a point, then translate it from one object to another. I know velocity of B, right? I can find velocity of B considering omega AB and RAB. And then B is part of AB, B also is part of CD. I can relate its velocity to this radius and IC, right? That's what we did before. So to do that, let me clean this stuff a little bit. So VB using link, we always start with the link that we have information about, link AB, right? VB is going to be LAB omega AB, which is going to be 3/12 times, what is omega? Omega is 2 times 2, it's going to be 0.5 feet per second. Correct? You guys follow this part? B is a part of AB, omega times this length, velocity. Now, using link BC, because remember B also belongs to BC. If B is a part of BC, this is center of rotation, this is radius of rotation, then VB is going to be omega BC times R BIC. How much is RBIC? Look at the geometry. The right angle, 45, 45. These two should be equal, right? Then RBIC should be 4 inches. And if you substitute here, we're going to get omega BC is VB divided by R BIC, which is going to be 0.5 divided by 4, 12. Remember, this is inch, it has to be feet. So it's going to be 1.5 radian per second. Okay, so I found this guy, and I'm just going to write the number in front of it. .5 radian per second, and highlight it with the yellow. Any question? Now I need to find also velocity of G. Look at here. I need to find velocity of G. The good thing with IC is that it allows me to directly go for the velocity. If you look at this length, you know what? Let me move G on top. If you look at this distance, this blue line, this is RGIC. And we need to find it. How you find that? How much is this length?
2 inches.
And how much is this length?
4.
4. So therefore, R, let me just remove those lines. So therefore, RGIC is going to be square root of 2 squared plus 4 squared. And that's going to be in inches, of course. .72 inch. Okay. Any question? I'm just finding the radius of rotation with respect to IC for each point I need. If that's the case, then V of G is going to be omega BC. Remember, this is still part of BC times RGIC. If you substitute 1.5 and 472 divided by 12, you get VG as 0.559 feet per second. So I have that guy too. I'm going to write it up here. VG is 0.559 feet per second, and I'm going to highlight it with yellow. Okay. So if you look at here, everything I needed for for this term, now I have it. I have M, I have VG, I have I have omega, everything. Okay. Any question about this? Now I'm going to go to equation 3. Let's just change this its color. I can make it black. Oops. So I try to use the color code so when you follow, you know what is what. So the first one, which was blue, was here. The second one, which was red, was here, of course, with all of this. Now the black guys. For 3, I'm going to continue here. For 3, that you have T of, I'm going to just write it again. T of CD is half IC omega CD square. I need I about C, and I need omega CD. I about C, look at here for a second. This is your link, right? This is your link, and your link rotates about fixed point. If you go to the back of the book, its I is similar to A, which was ml squared by 3. So I about C is going to be ml squared by 3. Its mass was 0.0776. The length is 5 and divided by 3. So 5 divided by 12 square times point. Yeah, there's 1 0 here. 0.0776 divided by 3 gives you 0.004491 slug feet squared. So I found this number too. The next thing to find is omega CD. And remember, not every problem is this complicated. I chose this because it includes everything, and it shows how you can, or actually you should, use your kinetics knowledge to go and find all the velocity terms, all omegas, velocity of G, any G if needed, okay? How you find omega CD? Are you guys done writing this? Okay, now please pay attention here. Again, point C is a part of BC and is a part of CD. If I get its velocity from IC, I can translate it to link CD, right? So the next thing I'm going to find is this. How much is RCIC? If you look at here, this is 4 and this is 4. So you get 4 square and 4 square root. You can find that, right? You guys follow? This is the right angle triangle. Both side angles are 45. So you can also use sine and cosine, doesn't matter. But if that's the case, technically a square root of 2 times 4 or 5 point something. 5.657 inches. Now, to find this, using again link BC, we can find velocity of point C, right? So VC is going to be omega BC times RCIC. Remember, the entire BC seems to rotate about IC, so you can find the velocity of any point. Any question about this? Again, look at here for a second, pause for a second, look at here. This link has this IC, right? So you can find velocity at any point. This point, you get the line. This point, you get the line. If it was continuing up to here, you can find the velocity of this point, just like that. Any point, you can find its velocity using IC. Now, I'm doing it for point C, and omega BC was 1.5, so you're going to get 1.5 times 5.657. So if you multiply this by 1.5, you're going to get 8.485. And the unit is inch per second, so I'm going to divide it by 12 to make it consistent. Point 707 feet per second. Do you guys get the same number? Okay. Remember, it's the same procedure all the time. Look at here for a second. I find velocity of C using this link. Then I'm going to go back to this link to find omega CD. Okay? So if that's the case, still we are doing the IC stuff, but now we switch to the part that we know. Now, using link CD, because C belongs to both BC and CD, VC is RCD omega CD, or omega CD is VC over RCD. Now, VC, we found it 0.707. RCD was 5 by 12. You should get omega 1.697 radian per second. I'm going to write it here, 1.697 radian per second, and highlight it like this. Any question? If you guys are confused or need more explanation, this is the right time to ask, by the way, right? Because I can explain it again. Don't feel shy that you don't want to ask questions. If you know how IC works, which was your quiz, I think you should follow this easily. Now, I'm going to go back here. You see all the terms I needed, I found. So the next part is substitute everything here, omega CD, ICD, MBC, VG, all of that, and find the T. I'm not going to spend time substituting the numbers, okay? Let me see if I can find this, the final number in. So technically, I'm just going to write the final equation once. T is half IA omega AB squared plus half MBC VG squared plus half IG omega BC squared plus half IC omega CD squared. This is if you substitute, you see, if you substitute, where is it? These three terms here, that's what you're going to get. Okay. Now you have all of the numbers. Let me see if I can find the answer somewhere. What is the problem number? 1811. So if you do all of that, your final T will be 0.0188 foot-pound, which is the same unit for energy. Double check these numbers, make sure you get everything right. And that's how it goes. Any question? Okay. So we're going to have at least 2 or 3 more examples next time. We're going to solve some of this so you're exposed to more of calculation of I, moment of inertia, the kinetic energy and everything. We have like 6 minutes left, and I don't think we can start or finish any of those problems. Therefore, I'm going to stop it here. Okay. And you had a quiz, so I give you 5 minutes of break. I think it's not a big deal. But you owe me 5 minutes if you want to stay longer, okay? In case we need. Any question or comment?
I have a quick question about the final.
Yep.
Is it gonna be comprehensive or I mean like,
Yes. My exams are always comprehensive. And the reason is this. I've told you guys, this is my policy in every class. Summer course is shorter, but no big difference. I always say, if you screw up a test at the beginning, a quiz, something, you know, now midterm was kind of late, and you improve your grades and your performance, I will neglect that initial part. To make sure you have improved, I have tested every student on every concept in the final exam, right? Because you may get 100% from final exam, which covers half of the book. I know nothing about the other half of the book. So if I want to implement that policy, which believe me, it's very helpful. I think I told you guys, I do not curve the grades. I look at individual performance, the homeworks, the bonus problems, you know, the quizzes, if it goes up and down, or if it keeps going up, or maybe it was up at the beginning and drop at the end. I look into all of that to see if I can help you, you know, a little bit to switch the grades. Because here's the thing. If someone, for example, gets 73, right? 73 is C. To get it to B, you need at least 7 points, right? If you have performed well, it may not get you 7 points to get to B. So 72, 3 to B is difficult. But if someone gets 76 or 7, and I realize that he dropped a couple of quizzes or she dropped a couple of quizzes at the beginning with low grade, but everything else is fine. If I kind of reduce the effect of those quizzes, which was like first, second quiz, that 77 or 76 or 78 could be kind of shift to B. That's how I do. So if you're close to the grade, borders, if call it that way, I can kind of use some of my authority based on your performance. Not, I mean, there's no other ways. I can't say, you know what, I like him, I don't like her, I like her. I can't do that based on, there's no difference between the students, right? The only thing is your performance. So if you improve, I will implement, or I will consider that improvement, that extra effort, because dynamics and most of the engineering courses are complicated, right? And you may have a plan to study, and in the first month, now this semester was 2 months, in a regular semester, 4.5 months, your plan of study doesn't work well. So you screw up a quiz, you get a bad grade, right? Or maybe like if it's a 2 midterms, 1 midterm, you didn't perform well. Then you realize that you have to make adjustment, you learn more. I can't punish you for the mistake you did, for example, in September when I'm grading in December, right? I try to consider this and help the students to improve. And this should be an encouragement for everyone to improve. So that's the case. The final exam has to be comprehensive. Now, dynamics is different because it's almost 1/2 particle, 1/2 rigid body. But most other courses, what you learn in chapter, I don't know, 1, 2, 3, 4, you're going to lose it later. So it's really difficult to say, you know what, I'm not going to test you from here back. So for all those reasons, my exams are comprehensive from A to Z. Let's see how it goes. Do you like it that way? Of course not. Right? But I think that is the right way to do, to make sure your learning has enough depth that can carry you. Remember, dynamics is a fundamental course. MEs are going to take mechanisms immediately. If you are MRE, you may go to robotics, or even you are mechanical, you may go to robotics and other stuff. So one part of mechanical engineering is based on dynamics, things that move, you know, it goes all the way up to very complicated cases, from like this humanoids that make to other crazy stuff, sending, you know, spaceships to Mars or somewhere. So the point is, dynamics is fundamental, and we have to make sure you learn good enough material out of this course to advance. Does that make sense, or I'm crazy? Or it makes sense and I am crazy, huh? At the same time. Okay. But that is how I do it. And I think, believe me, I have been teaching for many years. I work as an engineer for many years. And I have been college student for many years. So I'm very well experienced in all of those areas, believe me. So I think this is the best way to proceed, to make sure you guys get what you need and what you deserve as your education. Now we fill the 45 minutes, so you don't owe me anything. Any question? Any other question? Did you guys enjoy the lecture? Was it too fast or the pace was good? But, so by the way, I did not record last lecture, but because it was partially from halfway something, I found the lectures that, because I always record my, you know, online courses and keep them. I found chapter 17 from last year. I have done a couple of more examples, and because it was halfway through, I put the entire chapter 17 videos. There are 2 videos with more examples. I recommend you guys to go and watch them because there are more examples. You always ask for more practice and more examples. These are like 12 examples on video with the same class environment, different faces you may see sometimes if it comes to the side of the things, but that's not a big deal, right? So if you want to see more examples, please go and review them. Okay. Thank you very much. I will see you guys on Wednesday. I think on Wednesday we can finish this chapter. So I'm going to post the homeworks by Wednesday when we finish it, because you already have another homework. Now, again, as I said, you have 3 sets of homework from now till next Wednesday, right? And we have to squeeze them. I usually give the last chapter 19 less homework, but I don't like it because you need to practice, but we'll see how it goes, okay? Please make sure you start working on chapter 17 problems now. You finish it on time so we can go chapter 18 and 19 accordingly. Thank you all very much, and I see you on Wednesday. Bye.